Hey guys, it's George again. Okay, so now we'll be talking about summation and product notation. Now, a lot of you have probably heard or seen of that thing in math, but no one actually knows what it's called or what it's used for. It's just used as the stereotypical approach to higher level mathematics. So this right here is called capital sigma. Now it can be used to solve for finite sums and infinite sums and also represent integrals, mainly indefinite, which I'll get into later. Not in this video, of course, but later in my Riemann sum video. So let's say n equal to 1. So that is the lower bound in this expression. And let's say 4, that's the upper bound, not to be confused with, because summation means sum. Integral means distance across the grid. So let's say we had this and we had n squared plus 1. So how would we go around solving that? Well, the first thing we would do is we'd substitute our first bound in, then add the second bound, then add the third bound, and then add the fourth and last bound in this case. So what we're doing is we're substituting in the lower bound until we hit the upper bound. Now, I made a video about this last summer. It was 57 seconds long. I don't know how I did that. That is preposterous. Anyway, so this is going to evaluate to 1, or my bad. That's going to evaluate to 2 plus 6 plus 12 plus 20, I believe. Let's see. Yep. So we just need to add these up, and when we do, that is going to be the sum, or the finite sum, of this expression from bounds n equals 1 to 4. So, let's see if I can do this off the top of my head. So, 6 plus 2 is 8. I believe that's 40. Let me just check my math on that. Couldn't find the calculator, sorry. Yeah, that's 40. So the next type of summation that I'm going to show you is going to be infinite sums or infinite series. So you're going to see something like this. You're going to see n equals 1 or n equals 0 or n equals 2, something like that, to infinity. So let's say we had that 1 over 4n. So with this is going to be 1 over 4 plus 1 over 16. So it's going to keep repeating. It's going to be, you're going to plug in 1, then you're going to plug in 2, so it's going to be 1/4 plus 1/16 plus 1/64, and it's just going to go on to that until it's 1 over x to the nth. So what we're going to do in this case is we need to get it in r to the xth. So we're going to do 1/4, which is our r, or r to the nth, it doesn't matter. So infinite sum n equals 1, 1/4 n. So we use this formula, which is taking the r, in a sense, putting it up here, and then since n equals 1, 1 of 1/4 is just 4/4 minus 1/4. So it's going to be 1/4 divided by 3/4. So it's going to be 1/4. Just do keep, change, flip. Cancel those out. And so it's going to be the infinite sum n equals 1. 1/4 n equals 1/3. Now this might be kind of crazy to imagine, since you're not used to saying, oh, infinite sums has a finite distance, but that happens all the time in math. It might be weird to imagine, but it will approach 1/3. That is the essential limit of the question. Probably should have put this in my limits video, but it does have to do more with summation notation. So next thing I'm going to introduce, which probably no one has seen, on the contrary to this, is something that looks like this. So this is exactly like this. So it's n equals a to the xth. So let's say we just had that notation. A is the first term right up until a sub n or x. So it would be the same. We would put this on the bottom of this, and this is called capital pi, as you can see from right here, and the xth term of capital pi. So what capital pi means versus capital sigma is that instead of adding, you're multiplying. So you remember how with capital sigma, when I use n squared plus n, it was like 1 squared plus 1, 2 squared plus 2, dot, 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 dot. We added those. With capital pi, you're going to multiply those. So if I had, let's say, capital pi from n equals 1 to 5 2n. Let's say, actually, 2n squared over 4. So what we do with this is it would be 2, you're still going to treat this the exact same way you did with capital sigma, only this time it's going to be capital pi. So it's going to be that multiplied by 2 times 2 squared over 4, multiplied by 2 times 3 squared over 4, multiplied by 2 times 4 squared over 4, multiplied 2 times 5 squared over 4. So that would just be 1/2 And obviously I'm not going to simplify this because this is just ridiculous, but yeah, if you want to find a numeric value for that, go ahead. I know that would equal 1 right there. And I know 32 divided by 4 is 8. So the final answer for this, in its simplest form, would be 8 over 1 times 18 over 4 times 50 over 4. So in its simplest form, that would be this. So that pretty much concludes capital pi. You don't usually see capital pi as much in math as you do as capital sigma. However, capital pi can also be expressed. So let's say you had, I'm actually going to do how capital pi applies. So, say you have the capital pi, so let's say we had that. So it's going to be 1 over 1 times 1/2 times 1. It's going to look something like that. Now, we can compare this to, if you don't know what a factorial is, a factorial is pretty much like if we had, let's say, 3 factorial, that would be 3 times 2 times 1, which in a sense is what this is doing, because 3 factorial would be 6. So this would be theoretically the same as saying 1 over 5 factorial, I guess. Well, factorial down here, because that would be 1 over 5 times 1 over 4 times 1 over 3 times 1 over 2 times 1 over 1 until it eventually hit 0. But you don't multiply by 0, because anything multiplied by 0 is 0. So theoretically, that'd be 1 times 5 times 1 over 4 times 1/3 times 1/2 times 1 over 1. So theoretically, you could apply these two to each other. So that pretty much concludes the video. And I hope you learned a lot from it. Be sure to subscribe.